Organic chemistry. Now, organic chemistry is a very, very, very broad topic, especially to be covering in only one section of one tiny part of this course. But just be aware that we're just barely scratching the tip of the tip of the tip of the iceberg when it comes to organic chemistry. But just so you have an understanding of what you'd be getting into when you take an organic chemistry course, because I know you all want to. So, what is organic chemistry? Well, it's the study of compounds that contain carbon. Simple enough, right? Now, there are a few characteristics of organic compounds that I'd like to briefly mention. The first is that organic compounds contain carbon, and then they usually have quite a few hydrogens attached to it. So notice methane here in the bottom right. We have carbon with 4 hydrogens around it, and that's kind of a motif that you'll see repeated over and over again. Carbon or multiple carbons surrounded by a whole lot of hydrogens. Now, one thing that you should definitely remember is that carbon likes to form 4 bonds. Okay, now that could be 1 triple and 1 single, it could be 2 doubles, it could be 4 singles, it doesn't matter. But all that matters is that carbon always needs 4 bonds if it wants to be stable. Hydrogen, on the other hand, can only handle 1 bond. So you'll always see it kind of on the periphery of the molecule, whereas carbon likes to be front and center, right in the middle of any kind of organic molecule. Now remember that carbon can form single, double, or triple. So you can see here in this molecule, this is capsaicin, which is what's responsible for the spice in spicy food, if you are a spicy food junkie like me. Now, we'll go over what this actually means. This is called a skeletal structure here, but what I want you to notice is that there are some double bonds drawn in here, right, and then a whole bunch of single bonds throughout the molecule. So carbon can form double, single, triple, and a mixture of all the above. Carbon can also form long chains. Those chains can branch. They can actually even form rings. So for instance, you can see here we have caffeine versus theobromine. 2 very similar compounds, sometimes considered maybe like chemical cousins of each other. And caffeine found in a lot of cola drinks, found in coffee and tea and so forth. Theobromine is a chemical compound found in chocolate. And many people think that chocolate's high in caffeine. It's actually not. It's high in theobromine. In fact, the Latin name for the cocoa tree is Theobroma cacao, which actually means food of the gods. But anyway, we can talk about chocolate at a different time. But you'll notice that the chemical found in chocolate isn't caffeine. It actually differs a little bit. Notice on this nitrogen here, in theobromine, we only have a hydrogen, whereas here we have a CH3 group. So it seems like a minor difference, but when it comes to chemistry, especially organic chemistry, 1 or 2 or 3 or a small group of atoms can make all the world of difference between 2 compounds. So chocolate's actually extremely low in caffeine. There's more caffeine in a cup of decaf coffee than in a large chocolate bar. The next characteristic of organic compounds that we should discuss is the topic of heteroatoms. Hetero meaning different, right? So different atoms. Atoms other than carbon or hydrogen will be considered a heteroatom. This could be oxygen or sulfur or nitrogen or halogen like chlorine or bromine or iodine or fluorine. And it could be other atoms as well, but those are the common ones. And it turns out that when you have heteroatoms involved, these heteroatoms will have lone pairs, because remember the octet rule that everything wants 8 except for something like hydrogen. So hydrogen only has 1 bond attached to it, as you can see in each of these drawings. Hydrogen's attached via 1 bond to something. Carbon likes to have 4 bonds around it, and again that could be doubles, triples, whatever. And then something like oxygen actually has 2 bonds around it and then 2 lone pairs. Nitrogen will actually have 3 bonds around it and then 1 lone pair. Sometimes the lone pairs aren't drawn in when we are trying to kind of just summarize a structure. So just be aware that all of these atoms do have an octet except for hydrogen, which is a duet. So even if it's not explicitly drawn, it is there. Now, when we're drawing molecules, we've actually gone over a section on drawing molecules, and we've drawn these in 2 dimensions, but remember that these are actually 3D objects, so they can spin and rotate and so forth, and we can describe these molecules in terms of geometry, right, in different shapes. We can talk about the bond angles between the atoms and so forth, and this should all be a review. But just be aware that we're using VSEPR, valence shell electron pair repulsion theory, which just tells us that electrons are negative. Therefore, when two electrons get too close to each other, they repel. And so the electrons in one bond will repel the electrons in another bond or in a lone pair. And they'll try to get as far apart as physically possible. Now, in organic chemistry, you'll see a couple of kind of repeating patterns. The first is the linear geometry. This happens when you have like a carbon with a single and a triple bond, and you'll notice that the bond angle here is 180 degrees, so they'll get as far apart as they physically can, which happens to be on opposite sides of the molecule, and therefore a bond angle of 180 degrees. The next geometry that's relatively common would be trigonal planar geometry. This occurs when you have a carbon that has a double bond. So notice that each of these bonds here, well, in fact, all of these bonds over here as well, will each be 120 degrees, the corners of a triangle. Now, in a tetrahedral geometry, even though we draw the molecule like this over here, we sometimes are tempted to say that it has a 90-degree bond angle here, right? Looks like corners of a square kind of. That's not actually true. It's not a 90-degree bond angle, because remember that these are three-dimensional objects. And so instead, what we have is methane would actually look something like this, with the carbon in the middle, the hydrogens around it, making a tetrahedral structure. Kind of like a music stand, right, with the tripod legs and the music stand sticking up out of the top. All right, the bond angle between any two of these would be 109.5 degrees. All right, 109.5 degrees on any of these bond angles here. This is extremely common because, again, carbon often makes 4 single bonds, so you'll see a lot of tetrahedral geometries. Now, when we're drawing that tetrahedron in 3 dimensions, we can actually use some 3D drawing conventions for this. So we could go ahead and just draw it as, this over here, but that doesn't really give us the full shape, right? To try to visualize it and visualize kind of what's called the stereochemistry and the way that these are attached in 3 dimensions. So what's going to happen is anytime you have a solid line like this one and this one, that means that it's in the plane of the paper or the computer screen in your case. So that's flush up against the screen there. All right, now anytime you see a solid wedge like this one here, that means that the hydrogen there that's attached to it is actually coming out at you. So imagine kind of like one of those 3D images where it's supposed to be coming out at you. And then the little hatch marks, the dashed wedges, that means that it's going back away from you. So try to visualize that in 3 dimensions. It's a little tricky, but that's really how these molecules look. And so remember that these are 3-dimensional shapes. Now there are also a couple of geometries that come into play whenever we kind of alter a tetrahedral geometry. So the first occurs when we have a nitrogen usually, and this is called a trigonal pyramidal geometry. So notice that nitrogen has 3 bonds around it, and then it also has this lone pair. So we have 1, 2, 3, 4 electron groups around it, and so the electron groups go to the corners of a tetrahedron, but this lone pair is invisible. And so it turns out that we really only get this pyramid, this trigonal pyramidal geometry. It's like a pyramid with a triangular base, because we can't see this guy up here. But remember that even though we can't see it, it still takes up space. In fact, it even takes up a little extra space because those electrons are kind of free range, so they can go anywhere they want. They're not locked into a bond the way they would be in each of these bonds down here. And so it takes up a little space. It kind of squeezes the legs of that tripod together. So the bond angle is a little less than 109.5, usually about 107, but it depends on the molecule. So I'm just going to estimate that the bond angle will be approximately 109.5. And then if we have an oxygen present, will typically have a bent geometry. So remember that oxygen likes to make two single bonds, or it can make a double bond, but in the case of making two single bonds, again, we have one, oops, I just pushed the wrong button. There we go. All right, so in the case of oxygen, we have 1, 2, 3, 4 electron groups, right? So 1, 2, 3, 4. So just like before, they go to the corners of a tetrahedron, but just like before, these two groups are indivisible, and they just kind of take up a bunch of extra space. They squeeze together these two, arms here, and so making the bond angle probably about 105 or so, but a little less than 109.5. So again, trigonal pyramidal and bent geometries occur when you have a nitrogen or an oxygen present there respectively, and that kind of alters the shape of the molecules. Now, because organic molecules can be really large and complex, we have to come up with some different ways to represent these molecules. We could go ahead and draw out the entire thing over here, and sometimes it's worth doing that, but oftentimes we don't need that much detail. And so we could actually write what's known as the condensed structure. And so what we're doing here is I'm saying, okay, I have a carbon, and it's attached to 3 hydrogens. Right, so this group right here, the CH3, that's this group right here, CH3. Okay, and then I have a CH2 group attached to that, which is this CH2 group here. And then you can see that that keeps repeating with another CH2 group, another CH2 group, which are these ones right here in the middle. And then it looks like we have another CH3 group here on the end, and that's this one right here, CH3. So you can see how these directly map to each other. One thing that I do want you to remember, though, is that even though we draw this molecule this way, it does not mean that we have a carbon which is attached to the hydrogens, and then those hydrogens are attached to the carbon, right? The hydrogens are always on the periphery, on the outside of the molecule, and it's the carbons that form that chain, that backbone, down the middle of the molecule. Now, if we have a branch structure, oftentimes we will specifically write out or draw out the branch itself, just to let people know what's the shape. So here you can see we have a CH3 group, which would be this one here. And then it looks like we have a CH group, so a carbon with just one hydrogen attached. That would be that guy right there. Next, attached to that, we have a CH3 group up here on the top. So you can see that one pretty clearly. Followed by a CH2 group down here off of the main carbon backbone. And then to finish it off, we have a CH3 group on the end, which would be that CH3 group. So again, you can see how it directly correlates. This is nice because it allows us to kind of simplify the structure so that we can just see what's going on. Now, we can actually even condense these further so that we don't have to keep writing, CH2, CH2, CH2 over and over again. And so here's what we can do if we are really trying to squeeze things in a little bit more. I could go ahead and say, you know what, I have a CH3 group, which would be here, followed by 1, 2, 3 CH2 groups. So that would be this right here. And then I have a CH3 group on the end. Now you might be tempted to say, well, why don't I lump together these two groups to write something like CH3 with a 2 and then CH2 with a 3. I mean, that seems even simpler, but this loses all the connectivity, right? This would tell me that the two CH3 groups are attached directly to each other, and that's not the case. And so we don't want to draw it that way. Instead, we will typically draw, just this thing right here. We could do the same type of thing up here or down here on this next one. So notice that we have 1, 2 CH3 groups, and those are attached to this carbon right here, which is then attached to the CH2 and the CH3. So again, we can simplify this a bit further if we don't want to take up as much space as we normally would by drawing out the entire molecule. or if it's just a constant repeat. I mean, we could have 20 or 30 CH2 groups in a row. No one wants to write that. Ain't no one got time for that, right? So let's go ahead and look at an even simpler form of drawing molecules. The next method for drawing molecules, and to make it even simpler, is to draw what's known as a skeletal structure. So this really is kind of just the backbone of the molecule itself. And this is how it's going to work. Okay, so if you look down here at the bottom, anytime you have the endpoint of a line or the connection between two lines, so here and here, that represents a carbon. So that means I have a carbon here, a carbon here, a carbon here, a carbon here. So that means I have a grand total of 1, 2, 3, 4, 5, 6 carbons. You can see that I have 1, 2, 3, 4, 5, 6 carbons there in my backbone. It's drawn kind of in this zigzag pattern so that you can see where each carbon, where each carbon is. And also this gives us a better idea of the shape, because remember with that tetrahedral structure, it's not this big long spaghetti noodle. Instead it's kind of this wavy zigzag pattern. Now the next thing that we're going to do is we are going to assume that there are always enough hydrogens around each carbon atom on our skeletal structure to give it exactly 4 bonds. We call these implied hydrogens. So for instance, this carbon here, it already has 1 bond attached to it, right? So what I'm saying is that it actually has 3 hydrogens attached, because that would give it a grand total of 1, 2, 3, 4 bonds. And sure enough, over here we have 1, 2, 3, 4 bonds, and it's attached to 3 different hydrogens. Okay, this next carbon in would only be attached to 2 hydrogens because it already has 2 bonds attached to it. And sure enough, over here, it's attached to 2 hydrogens. All right, so those are called implied hydrogens. It's just implied that we always follow the octet rule, that we always give carbon 8 electrons, right, or 4 bonds. Now, there are some times in which case we'll actually have a heteroatom there. So, for instance, if I had a heteroatom attached here, like an oxygen, I would go ahead and specifically draw out the oxygen as well as the hydrogen attached to it. Or let's say I had a nitrogen here. I could go ahead and specify that I have nitrogen and a couple of hydrogens attached to that. It would actually be NH2. All right. So that would be, how I draw these things. So let's actually go ahead and practice, because I think that's the best way to see this in action. So here I have this lovely little pentagon, but what does it really mean? Well, what it's really saying is I have 1, 2, 3, 4, 5. So in essence, I actually have 5 carbon atoms that are arranged in a ring. And so that's kind of the backbone there. And then it implies that I have enough hydrogens to give each carbon exactly 4 bonds. So notice I've given it 1, 2, 3, 4 bonds, right? Erase those because it makes it look like double bonds, which means that this carbon also must have 2 hydrogens attached, 2 implied hydrogens over here as well, 2 over here, and 2 over here, because that way each and every carbon has exactly 4 bonds, which is what it needs to be a nice stable molecule. Let's go ahead and try another one. This one includes a heteroatom. So what do we have? Well, we have 1, 2, 3, 4 carbons. Some people are tempted to draw an extra carbon up here, but that's not true, because remember, this line is just saying that it's going to this oxygen atom there. So 4 carbons, 1, 2, 3, 4, all single bonded together. It looks like on the second carbon from the left, I need an oxygen with a hydrogen attached to it. Okay. Now I can go ahead and add in the implied hydrogens. So this carbon over here on the far left, it only has 1 bond, so it needs 3 more bonds, each one to a hydrogen. What about this carbon? Well, it already has 3 bonds, so it really only needs 1 more. This carbon needs 2, and this carbon needs 3 bonds. And so therefore, we've given every carbon exactly 4 bonds. Everybody's happy. Now let's try going the opposite direction, where I give you the the full structure, and then you go ahead and write out the the skeletal structure. So what I would do personally is I would go ahead and just figure out the backbone. So I have 1, 2, 3 carbons in a row. All right, so I'm going to go 1, 2, 3 carbons in a row, just like that. Now it looks like on this second carbon we have a carbon coming up and a carbon coming down. So I'm going to go ahead and write a carbon coming up and a carbon coming down, just like that. On this carbon on the very end, it looks like I have an oxygen with a hydrogen coming off. So I'm going to go ahead, actually, just so you can see that it connects, oxygen with a hydrogen coming off. And that's it, right? And so I didn't have to draw in all of these hydrogens because they're already implied, that they're right there in the structure. Kind of nice, right? Let's go ahead and try another one, just to make sure that we have this down. Okay, so let's see. This one I'm actually going to go ahead and write these out. This is 1, 2, 3, 4, 5, 6 hydrogens. So 1, 2, 3, 4, 5, 6 hydrogens. It looks like on carbon number 2, I have an OH. It's drawn, going down here. I could either draw it going up or down. It really does not matter. Okay, so there's that, because this is 3-dimensional, so I could rotate it. It looks like on carbon 3, so I'm actually going to erase this just so you can see that I could actually draw this OH going up. Okay, perfectly fine, either direction. And then on carbon 3, it looks like I have a CH3 group that's branching off, so there's my CH3. Do I need to go ahead and draw CH3? Well, no, some people do, just to specify, but technically it's implied that since that's the end of a line, there's already a carbon there, and because it only has 1 bond, it needs 3 hydrogens attached to it. So it's already implied that that's the CH3 group. So that would be my molecule right there. Much cleaner than trying to draw out the entire thing. All right, so the next thing involves Star Wars, right? So in this case, if you're looking at these toys, battle simulation miniatures that I might just happen to own. I don't know. Anyway, so if you look at these, you can probably tell if you've ever seen the movies, and if you haven't, you totally should. That's your next assignment. Go watch the original trilogy. But anyway, so if you look at this, you can probably recognize, that looks like Darth Vader on the left, even without looking at the little name tag at the bottom, and Yoda is over on the right. And the reason you can tell this is because you look at it and you can recognize certain characteristics, like, oh, Darth Vader dressed all in this black armor stuff, Yoda's got, green skin, he's short, and, hairy ears and so forth. And so you recognize those, and then because you recognize, those traits, you can actually, predict some stuff about those characters, right? You know that Yoda is going to talk funny, that he, is going to make you try to lift, spaceships out of the swamp and so forth. Darth Vader is going to, speak in a weird, raspy voice, and all the time, and that he will probably throw you down an elevator shaft and things like that. So it turns out that functional groups are going to do the same thing. These are groups of atoms that we can recognize, like, hey, that's an alcohol group. And so then once you recognize it, then you can predict things about the chemical, even though you've never actually, maybe even seen the chemical before. You can predict certain characteristics about it based on which functional groups are within that molecule. So let me give you the full definition of a functional group. It's an atom or a group of atoms with characteristic chemical and physical properties. It could have a multiple bond, it could have a heteroatom, it could have both, but typically what we're going to write is we're actually going to write this as R, and then attached to some kind of functional group. And this R just means the remaining portion of the molecule. I always think of it as the rest of the molecule. So this could be, it could be one carbon, it could be like 100 carbons, it could be some super complex structure, and then it's going to be attached to a functional group. So let's go ahead and look at the simplest functional groups. These are the hydrocarbons. As the name implies, hydrocarbon, they contain hydrogen and carbon. And they only contain hydrogen and carbon, no heteroatoms at all in there. Now, there are alkanes. These contain only single bonds, right? Carbon-carbon single bonds. Alkanes, notice the A-N-E ending there. So that specifies that you only have single bonds. We're not going to go into any nomenclature, but when you do take organic chemistry, you'll find out that, if you have something like hexane, the hex means that there are 6 carbons. The A-N-E ending tells you that they're all single bonded together. If I have something like ethene, then eth means that there are 2 carbons, and the E-N-E ending tells you that it's an alkene, that it contains a carbon-carbon double bond, or at least one carbon-carbon double bond in there. An alkyne, so if I had something like heptyne, the hept would tell me that there are 7 carbons in the structure, and the Y-N-E ending would tell me that it has a triple bond in there. And then there's one kind of special group. These are the aromatic hydrocarbons, and these contain a benzene ring, which is kind of a weird thing. It's this 6 carbons in a row with alternating double bonds. And these are a little bit special because you might say, well, why are they any different than just having an alkene, right? Because there's a double bond. Well, the reason they're special is because of these alternating double bonds. Remember when we were drawing molecules, and I mentioned that if you could draw more than one valid Lewis structure for a molecule, it exhibits resonance? Well, that's exactly what's happening here. I can draw these 2 different structures for benzene, and really all I've done is rotated the double bonds a little bit, right? And yet those are 2 different drawings for the same molecule. So the actual benzene molecule, or the benzene ring, is actually a hybrid of the 2. So instead of having single double single double single double bonds, you actually have 6 identical bonds, and they are all the strength of about 1.5 bond. And so these behave differently than a normal alkene. So it gets its own functional group. Now, moving along with the functional groups, let's start looking at those that contain heteroatoms, so something beyond just a hydrogen and carbon containing molecule. So the first one would be the alkyl halides. Remember, halide means that it's from the halogen group, so fluorine, chlorine, bromine, iodine, column 7A. We typically just abbreviate that X. X just means any halogen. So the simplest would just be, R, that's a single bonded to an X, right? So this would be X that's attached to the rest of the molecule. And in this example over here, the rest of the molecule is just a CH3 group, but it could be any length. But the important part is this right here. So that tells me that it's an alkyl halide, and it's going to behave in a certain way. Alcohols, this is something that everyone's familiar with, right? So alcohols have this OH group attached to the rest of the molecule. Now, this one right here, this OH is attached to what we call a methyl group. So this is methyl alcohol or methanol, sometimes called wood alcohol or sterno. You drink this stuff and you go blind and then you die. So you don't drink this one. If this were actually attached like this, CH3CH2OH, then this would be ethanol or ethyl alcohol, which is drinking alcohol. Very different chemical, right? You don't typically go blind by drinking ethanol. The next functional group that we have is called an ether. So an ether will have a carbon chunk and then a single bonded oxygen, and then that will be bonded to another carbon chunk. So it goes R, O, R, just like that. So in this case, I have a methyl group, and then this oxygen in the middle, and then another group. These 2 groups here could be different. It does not matter, right? One could be a super long chain, and then have the oxygen here, and then this one could be just a short thing. And this would still be what we call an ether. If you've heard of the term ether before, you're probably referring to diethyl ether, which is commonly used in hospitals. It used to be used as an anesthetic, and now it's actually used as, like if you ever go in for like a sleep study or something, and they put those little electrodes all over your head, and they have the glue on there, they'll often use ether to help remove that. It dissolves things very well. But it's also super highly flammable, and it smells kind of funky. So, all right, the next would be amines. Now, amines are kind of weird. So, this is where you have a nitrogen within your molecule. And it could be a nitrogen with 2 hydrogens on it. It could be a nitrogen with just 1 hydrogen, or it could just be a nitrogen. Now, notice here I'm attached to 1 carbon chunk. Here I have 2 carbon chunks, and here I have 3 carbon chunks. So remember that nitrogen likes to form a total of 3 bonds. So it could be all 3 bonds to carbons, could be 2 bonds to carbons, and 1 to a hydrogen, or 2 to hydrogens, and 1 to an R group. And so here you can see that we have an amine because we have an NH2 group attached to this carbon chain right here. Let's see. Amines typically smell pretty bad. Triethylamine is like the smell of rotting fish and so forth, so not terribly a good smell. Now, several different functional groups will actually contain this thing called a carbonyl group. And a carbonyl group is going to have a carbon in the center, and this is going to be attached to some R groups, some other chunks of the molecule. But the important part is that it's going to have this double bond to an oxygen atom. All right, so it could be some long complex molecule, and then it has this carbonyl group, and it could be going on forever. It could branch. It does not matter. All that matters is this thing, the carbonyl group, right there in the middle. So let's go ahead and look at the functional groups that contain a carbonyl group. So here we have the aldehydes. So the aldehydes have the carbonyl group at the end of a chain. So looking over here, we have a long chain, and then here's our carbonyl carbon. And notice that the only thing attached to that at the end would be a hydrogen. That's it. So really this is at the very end of the molecule. A ketone, on the other hand, is going to be in the middle of a molecule somewhere. So here's our carbonyl carbon, but notice that in both directions it has carbons coming off of it, right? Whereas the aldehyde only has it on the very end, where you have only a hydrogen after that. Next we have the carboxylic acids. So some organic compounds are still considered acids. This one right here is known as formic acid, and this is what bees and ants inject when they bite or sting you, and so you can definitely feel it burning, and so it's an acid, and it's because this hydrogen can actually come off. It's ionizable, and so that's what makes it a hydrogen, if you remember the section on acids and bases. But to make something a carboxylic acid, you need a carbonyl carbon, and then it has to be attached to an OH group. So this is going to be on the end of a molecule, and it's always going to be carbonyl group and then OH group. So it's going to always have that pattern. Now, you might be tempted to say, well, isn't this like an aldehyde, and then this is kind of like an alcohol? No, it does not work that way. You don't have an alcohol and an aldehyde. Instead, you just have one functional group, and it's considered a carboxylic acid because it behaves very, very differently than the, just the normal alcohol and aldehyde. Now, carboxylic acids typically have a very strong odor. So something like vinegar is acetic acid or ethanoic acid, and it has a very strong odor. Butyric acid or butanoic acid is the what's responsible for the smell of BO. Right? It's what bacteria produce when you're sweating and they sit there and churn out butanoic acid. And also it's the smell of rancid butter. So a lot of really kind of strong, unpleasant odors. I personally like the smell of vinegar. I put vinegar on everything, my baked potatoes, on my pizza and stuff, but a lot of people don't really like that smell. Esters, on the other hand, typically have a very, very good smell. So this one over here on the right, this is ethyl butanoate, and this actually smells like pineapple, which is really nice. So how do you know you have an ester? Well, what you're going to have is you're going to have the carbonyl carbon, and then you have this OR group, right? So here we have a carbonyl carbon, and then we have this oxygen, and then we have some other carbon chain attached to it. So notice that this looks a lot like a a carboxylic acid, right? Except the difference is instead of having hydrogen here, you actually have an R group, another carbon chain attached to it. And this isn't coincidence. In fact, esters actually, you can produce these from carboxylic acids. It's one of my favorite labs. You take carboxylic acids and alcohols, and with a little acid catalyst in there, you can actually change them into esters. And so the lab starts out smelling really, really bad, like vinegar and BO and everything. And then as the reaction progresses, it starts to smell like cherries and wintergreen and pineapples and bananas and all these delicious smells. Now, one thing to note though is that whenever I do this lab, people always ask like, "Oh, this smells so good. Can I, take some of this home and put it in my lotion or something?" And I wouldn't recommend it because esters can actually break back down into the carboxylic acid. And so that actually would be a pretty good April Fool's Day prank to play on someone, to give them this lotion that smells like strawberries or bananas, a very lovely fruit smell. And then they put it on, and then over time, the the esters would start to break down back into the carboxylic acids, and they start to smell like really nasty, rancid BO. And then they'd be like, oh man, this is nasty. I got to put some more lotion on to cover it up. And then it would just make it worse. It'd be horrible. So I guess you could do that. It'd be kind of mean. So what are the last couple? Well, here we have the amide or the amide, depending on where you're from. And so in the amide group, this looks a lot like this last one, the ester, right? Except the difference is instead of having that OR group, we actually have a nitrogen. So this, again, is not considered an amine plus an aldehyde. It doesn't work that way. What we do have is we have this carbonyl attached to some kind of nitrogen group, all right? And that could be a nitrogen with one hydrogen or two hydrogens or zero hydrogens on it. It really doesn't matter. It's that nitrogen attached, that's directly attached to that carbonyl carbon. So here you can see that we have our carbonyl carbon, and then we have this nitrogen group attached to it. So that's an amide. If you go into biology, you study a lot about peptide bonds. They're actually technically just amide bonds. Really, all you have is you have a bunch of amino acids, and so an amino acid has an amine group on one side that has an NH2 group, right? And then on the other end of the molecule, it has a carboxylic acid group, which looks like this. And when those different amino acids come together, you can actually make bonds between the amine and this carboxylic acid group, and you can make an amide bond or a peptide bond. And that's how you start to string together amino acids into proteins. All right, so let's go ahead and practice, and let's take a look at some functional groups within an actual molecule. So this molecule here is procaine, which is a chemical derivative of cocaine, and you can see that there are a bunch of different functional groups present here. So what do we notice? Well, it looks like this right here, this NH2 group, that's an amine, right? We also have an amine over here. So notice that it's a nitrogen. This time it doesn't have any hydrogens on it. It's just attached to 3 different carbon groups. But that's still perfectly fine. It's still considered an amine. Now, what else do we have here? Well, here in the middle, it looks like we have a carbonyl group directly attached to an O that's then followed by some more carbon chains. So carbonyl carbon directly attached to like an OR, that would be an ester. Okay, do you see any others in here? Well, it looks like this thing. What's that when we have like 6 carbons in a ring with alternating double bonds? That would be a benzene ring. So this would be considered an aromatic group, right? Or a benzene ring, whichever you
prefer. Benzene by itself is just this ring, and then we can obviously attach different things to it. Alright, so that helps to look at the functional groups themselves, and hopefully you can look at a chemical compound and you can start to realize, like, oh yeah, that's an ester. That will probably smell nice. Or, ooh, that's a carboxylic acid. That's going to be acidic and probably has a strong smell. This is an amine, and amines don't typically smell very good, right? I mean, there's like cadaverine, which smells like cadavers, and putrescine, which smells like putrefying flesh, which, if you ever anger a chemist, they might sprinkle a little bit of that in your car, and then your whole car smells like putrefying flesh. So anyway, you can predict certain things about it. But let's look at some general properties of organic compounds and see if that helps us to understand how these functional groups really are useful when looking at overall properties of a molecule that you may never have seen before. So, for instance, organic compounds, we know that they have weak intermolecular forces. Right? They're not ionic, so these often have only dispersion forces, or sometimes dipole-dipole forces, or occasionally hydrogen bonding. But that means that overall, organic compounds will have low melting points, low boiling points. Many of them are liquids or gases at room temperature, and of course there are exceptions to this, but generally they are larger molecules with a lot of heteroatoms in there. But a lot of basic things like gasoline is an organic compound, right? And it has a low melting and boiling point. It's a liquid at room temperature. Methane, which is natural gas, or propane, again, very low melting points and boiling points, and they're gases at room temperature. Now, why is this? It's because all of those carbon-hydrogen bonds within an organic molecule are completely nonpolar. So therefore, your overall molecules will be nonpolar as well. If it only has carbons and hydrogens, if it's a hydrocarbon, it's guaranteed it will be nonpolar. Now, if you do throw in some heteroatoms, then you can actually make it into a polar molecule by kind of, those heteroatoms have different electronegativities, which can lead to polar bonds, which can lead to an overall polar molecule. But just remember that there's a rule of thumb that like dissolves like, and because water is an extremely polar molecule, and most hydrocarbons, or most organic molecules, are nonpolar, therefore they don't mix, right? Think of gasoline on top of water, right? No matter how much you kind of stir it, it's still going to separate. Or salad dressing, which contains vinegar, which is mostly just water mixed with vegetable oil. One is polar, one is nonpolar, they just don't mix. However, nonpolar molecules dissolve very nicely in each other, which is why you can use gasoline to clean the grease off of your hands after working on your engine, because they're both nonpolar and they dissolve in each other. So let's go ahead and predict whether these molecules will be soluble in water or not. So again, what we're looking for is we're looking for a lot of heteroatoms that would make something polar and therefore soluble in water, especially if there's a very short carbon chain, because those carbons and hydrogens will be nonpolar. So in this first example, this is hexane, and it's definitely not going to be polar at all, right? It's completely nonpolar, would not dissolve nicely in water. What about this second one? Well, it does have some carbons and hydrogens over here, right? But it does have an OH on the end of it, and so therefore this would overall be a relatively polar molecule and should dissolve nicely in water. And in fact it does. I mean, this is ethanol, or drinking alcohol. It mixes very nicely with water. What about this one here on the bottom? Well, this is a whole lot of carbons and hydrogens. It does have one OH group here at the bottom, but that's one puny little OH group compared to this massive, molecule. And it turns out that this, overall will not be polar, and so it won't dissolve in water. In fact, that's cholesterol, and so that's why cholesterol will actually precipitate out. It separates out of your blood, and then it kind of lines the walls of your arteries and so forth, and can lead to massive problems. Now, if we're talking about solubility, we might as well talk a little bit about vitamins. So vitamins are organic compounds. They're needed in small amounts in order for us to survive. We cannot synthesize them in our bodies, so we have to actually get them in our diets. Some are water soluble, some are fat soluble. The water soluble ones are a little safer because you can, take a whole bunch of them and you just excrete any excess that your body doesn't need in your urine, right? You just excrete it in your urine. You may have expensive urine because you just wasted all those vitamin tablets, but you can't really overdose on it. However, the fat-soluble vitamins you could theoretically overdose on because those are dissolved in your fat and in your liver, all that fatty tissue, and so your body doesn't really have a way to flush it out. So if you were to take far too much, it just keeps dissolving in your fatty tissue and in your liver. There's nothing your body can do, and so theoretically you could actually overdose on them. So let's take a look at vitamin A, because I can never remember which ones are fat soluble and which ones are water soluble, but if you look at the structure you can predict it, right? So vitamin A, this is sometimes called retinol. It's important for the receptors in your eyes. It's also important for your skin and mucous membranes and so forth. An important vitamin. Now, will it be water soluble or fat soluble? Well, let's take a look at it. Here we have a one chunk that is water soluble, right? I mean, that's a polar portion. But what about the rest of the molecule? Is the rest of the molecule going to be polar or not? Well, look at this thing. This whole thing is one very, very non-polar group, right? And so overall, this is going to not be soluble in water because this little tiny OH group simply can't overcome the lack of polarity of the rest of the molecule. So this is going to be a fat-soluble vitamin. What about vitamin C, or ascorbic acid? Okay, this is important for the connective tissue in your skin, and it also helps to prevent scurvy. So the early pirates and sailors didn't have access to fresh fruit, and so they would sometimes develop scurvy, and really nasty, your teeth fall out and all kinds of stuff. So make sure you get enough fresh fruit and veggies in your diet. But anyway, let's try looking at this thing. Well, where are our heteroatoms at? Oh, I've got one here, and here, and here, and here, and here, and here. Now, it is true that there is some carbons in here, but it's a pretty small carbon chain compared to the 1, 2, 3, 4, 5, 6 different oxygens that are in there. Overall, a very polar molecule, which means it should dissolve very, very nicely in water. So as you can see from this overview of organic chemistry, you don't need to know everything about a molecule in order to make a few predictions. You should be able to kind of look at it and look at the functional groups and decide whether it will be soluble in water or not, how it might react and so forth. And if you go into organic chemistry, you really start to discuss the reactions and how they work. Some very interesting things, but this was just for an overview on how to kind of make some predictions about some general classifications. So let me finish up by showing you something a little bit that might be a little bit fun.
All right, do you like to travel? I certainly do. Unfortunately, I don't get to very often. But what I do is I have this little briefcase, just in case. Kind of handy. You can't fit much luggage in here, but it's nice because I have a bunch of business cards in it. And these are actually business cards from a variety of hotels, and so sometimes when I'm feeling down, I actually just kind of go through and be like, oh, I'd really like to go to the Hotel Dante, or ooh, the Zenner Hotel, that sounds like a lot of fun. Maven Hotel, that would be great to visit in Las Vegas. And so what I'm going to do is I'm going to actually have you pick one of these, and I'm going to see if I can predict which one you picked, right? Now, normally I'd have you do this, face to face. So I'm just going to, kind of practice here. Have you choose anyone? No? Okay. I can mix it a little bit more. Literally, you could tell me when to stop whenever. Okay, so let's say you choose this one. I won't look at it. All right, you go ahead and look at it, and just put it back in the deck. Now, it turns out, though, that I can actually predict that you decided to go to the Plaza Hotel, which is in Tel Aviv. Now, you might think I'm cheating because this is all on, a video, but, it really works. In face-to-face, we could do this. But just to prove it to you, I'm going to go ahead and I've been to one hotel. Okay, I'm going to have you make the prediction this time. So here, just so you can see it, it's right there. I'm not going to mess with it. I'm going to go ahead and take these cards and I'm going to mix them up again, and you are going to go ahead and choose which hotel I've been to, and we'll see if you're right. Okay, see if you've learned how to predict things based on the characteristics of organic compounds, right? So here, this is the one. You could have chosen any hotel. You could have chosen the Wave Hotel, but you chose this one right here, and that would be the Bentley Hotel. Okay, that's a nice hotel. And so if I go ahead and put these back, if I open this up, you can see that I haven't messed with it, right? It's been sitting here the whole time. And inside is one thing, and it looks like a little key card. You're not supposed to take these, but anyway, from the Hotel Bentley, right? And so luckily, you've been able to predict, where I've been, right? Simply based on some cards. And so even though you may not have ever seen me on vacation or anything, you can still make some predictions. Just like with organic compounds, even though you may be faced with some brand new organic compound you've never seen before, you can actually make some predictions about it based on your knowledge of just simple chemistry and the organic chemistry that we've been discussing. So I hope that this has been enjoyable. Thanks for staying tuned the entire time. All right, I hope to see you sometime. Bye.